Right, I'm going to talk about using Cooper pair to explain superconductivity. So first, I shall list the properties that I hope to explain using a semi-empirical model of Cooper pair. We'll start with the property that a superconductor has zero electrical resistance. This is probably the property that is most difficult to explain. Followed by number 2, Meissner's effect. Just the Meissner effect. This has in fact been explained by London, as I described in an earlier video, but there was one question that was left dangling. That was that how the electrons can all go to the same state and form a single giant wave function. Electrons go into same state. How is that possible? Okay. The next item number 3, that would be the property that there is a critical magnetic field. And what this means is that if we apply a magnetic field to a superconductor, if we increase the magnetic field, there comes a point where if the field is big enough, it will destroy the superconductivity, meaning that if the magnetic field is big enough, the superconductor will stop being superconducting. It will become a normal conductor again with resistance. So this is a critical magnetic field. Question is, why would a magnetic field have such an effect? Okay, next item. Now the next item here is this. Is the property of the heat capacity. Alright, for the heat capacity, the property is like this. Suppose that I have a normal conductor then if we imagine plotting the heat capacity against temperature for a normal conductor, we know what it looks like. It would be a curve that is described by by the expression a constant times the temperature plus another constant times the temperature cubed. So we've learned earlier that this term comes from the electrons, that term comes from phonons. There are these two contributions that we have learned. That's a normal conductor. But it is found that when the normal conductor falls below the transition temperature of the superconductor, right, the normal conductor would become a superconductor, and it was found that below this temperature the shape of the graph becomes very different from this formula. Instead of following that same curve, it would now look like this. Right, it will follow a different curve instead. Okay, and this curve is described by another equation that goes as C equals to e to the power of minus, let's see, I've got exp bracket minus a certain number that I call delta divided by kBt, and there could be a constant in front. Now if you look at this expression, it looks familiar. It looks just like the Boltzmann distribution, where the delta there takes the place of some energy E. So what this seems to suggest is that below Tc, below the transition temperature, there is something in the superconductor that makes the electrons behave as if they follow some kind of a Boltzmann distribution. And we know what Boltzmann distribution looks like conceptually when it has this form. It means that there would be, in this case, two energy levels that are separated by delta. Okay, so that this expression here might represent the probability of or the relative population of the electrons in the two levels. So in that sense, there is an energy spacing of some sort. Okay, for this reason, the delta here is often called an energy gap. Now at this point, it can only be an abstract idea. Alright, this is some kind of energy gap is what this measurement of the heat capacity suggests, but as it is based on just this observation, there is no idea what might cause this energy gap. So that's one of the things that we hope to explain. Okay, and number 5. Number 5 would be that the superconducting transition temperature, it depends on the isotopic mass of the superconductor. Now what this means is as follows. Consider, for example, mercury. So an experiment that measures the heat capacity, that measures the superconducting transition temperature for mercury has been carried out for a few different isotopes of mercury. Isotopes ranging from one with mass number 200, 201, 2 and 3 to 203. So there are these three isotopes of mercury. The superconducting temperature has been measured, and it was found to decrease with increasing mass of the isotope. Okay, so the temperature sort of ranges between 4.12 and 4.16 Kelvin or so. So this was what has been found by experiments. And it is this last result here which suggested that superconductor might have something to do with the vibration of the atoms. Because how else could the transition temperature depend on the isotopic mass if it is not because the mass are somehow moving and perhaps colliding with the electrons? Now this idea that the movement of the atoms is involved is often described in terms of phonons. Because phonons are the quantized wave of atomic vibration. So we sometimes think, well, we could say that the electrons somehow interact with the phonon. So there's some kind of electron-phonon interaction. But for this discussion, we are not going to talk in terms of phonons. We are just going to talk in terms of displacements of the atoms. So starting from the idea that the electrons can cause the atoms to be displaced, we shall describe how this leads to the idea of a Cooper pair, and from there how to explain each one of the earlier properties. So let's start with the picture of the atoms in a metal. And just draw these few neighboring atoms. Now we think of each atom. We think that each atom would contribute, say, one electron that can conduct electricity, and this electron can roam freely around the metal. And if it does so, it leaves behind a positive ion. So we are going to think about a picture of this metal as positive ions in a sea of electrons. And that's often how we would describe it in high school chemistry. Alright, so now suppose that there is an electron. Suppose that we follow an electron as it zooms past in between these ions. Okay, so for example, that might be an electron. It zooms past these ions with a certain velocity v. Suppose that at this instant it is here. Then it would exert an attraction on the two nearest ions. So as a result, these two ions would move slightly. Now the effect of these two ions moving slightly, alright, as they come closer together, is to create a region of slightly higher positive charge. And as a result, if there is another electron, of course there are always electrons, as a result it would become attractive to, say, another electron nearby. So this electron might be, and if this electron happens to be moving along close to the same path as the first electron, it will experience the resistance of these two positive ions as they move slightly closer together. So that's the idea. Okay, now then, what we are going to do then is to estimate the attractive potential resulting from this movements of the ions. Now we're going to use a very simple approximation. Suppose that this ion moves up, gets displaced by a distance delta. Okay, so that would be, say, the distance from here to there, a small distance. And an electron which is around here will experience a change, a positive potential. All right. Now, normally, if the ion is not displaced, the electron would not experience any positive potential because the positive charge here would be effectively cancelled by the surrounding electron cloud. But if this positive ion is displaced slightly, then that changes the arrangement, and there would be a net positive potential in this region that is given by the change in the Coulomb potential due to this positive ion for an electron at that point. Now, this electron will experience the attraction from this displaced ion when it is somewhere in this neighborhood. As the electron moves further away, any net positive charge around here, all right, would attract the surrounding electrons that would come around and screen out the effect of this ion on electrons that are further away. So what we're going to do is, suppose that this interatomic distance is d. Okay, we're going to suppose that when the electrons, only when the electrons come within a range of the order of d from a particular positive ion, will it experience the attraction from that ion? Okay, so the Coulomb potential then, that is due to this ion, is given by 1 over 4 pi epsilon naught times, let's see, E squared, that will be the charge of the ion and the charge of the electron, over R, which is the distance of the electron from the ion. Okay, so as I said, normally when this is not displaced, the surrounding ions, the surrounding electrons will be enough to cancel any attraction on the passing electron. But because this is displaced, the change in the potential, would not be cancelled, and that gives rise to the positive potential. Now to find the change in the potential, we shall use the small change approximation, which is given by du by dr times delta r. Okay, right, I can see that this delta is going to be confused with that. So let me just call it the normal d. Okay, the normal d. And in this case, the dr here is the normal, is the delta. The du dr would be obtained by differentiating that. So that gives minus E squared over 4 pi epsilon naught R squared. Okay, and we're going to say that because the electron would experience this attraction when it is in its neighborhood, we're going to assume a typical neighborhood of about with a distance of about d. Okay, so somewhere when the electron is somewhere around here, its distance from a positive ion would be would have a distance of the electron will experience the attraction when it is within a range of about d. So we're going to say that this is approximately this the order of E squared 4 pi epsilon naught with the R replaced by D. So that's the attractive potential. Alright. Now, and this is the potential that we want to try and calculate. Because if we know what this potential is, we would in principle be able to solve the Schrodinger's equation and obtain a wave function for the electron that is attracted to this positive potential that has been created by this other electron. Okay, so in effect, we would be able to obtain a wave function for this pair of electrons, which is what the Cooper pair is about. Now, in order to calculate a number for this change in potential, we need to know delta. Now, D here is the interatomic spacing, which is usually known for typical metals. We can always look it up in Google or some table of constants. Now, and let me call this potential V. Okay, so let's think about how to find delta, the displacement of the ion. So this is something that we don't know, and it depends on this delta movement of the ion. It depends on a subtle way on the movements of the electrons and the property of the ions itself. So here's what we can do. For a start, let's think about the force that this electron would exert on the ion. Okay. Now, this point that there is a possibility of confusion. So let me say again what we're trying to do. We have an electron that zooms past it, and this and its attraction on this ion will cause the ion to move up. Okay, and this upward movement creates a region of positive charge around here that would attract another electron. So this potential that I'm talking about is really the potential that would act on another electron when that electron comes over here. Okay. Whereas this electron itself, as it zooms past, right, it would then move away, and we're interested to calculate the force that this electron would have on this, and the amount, and then the amount, the distance delta that that ion would move. So the force due to that electron is given by a similar expression to that. It would just be the Coulomb force. F equals to E squared over 4 pi epsilon naught d squared. Alright, when the electron is around here, its distance from the ion is of the order of d. Alright, the distance range within which it can attract this ion. As it moves further away, its attraction will be screened out by other electrons that move around it. Okay, so that's the force. Now, if we know the force, right, we know so we have an estimate of the force. We can also have an estimate of the time that this force would act for. Alright, because as I said, when this electron gets further away, its attraction will be screened out by other electrons. So it's only when this is within a range of about d that its attraction is felt by this ion. So we could say that the time that force will act for is roughly the time for this electron to travel by a distance of about d. And since we know that in terms of the velocity v, that time, let's say tau, would be d over the velocity. And we would also know how to find the velocity if we assume that we're talking about electrons in the Fermi level or at the Fermi level. Now I have to justify later on why we want to think about electrons in the Fermi level and not electrons which are further down. So for now, let's take this to be the Fermi electron. So then the velocity would be related to the Fermi energy simply by half mv squared equals to EF. Because EF is just the kinetic energy of the electron. So what we have now is we now have a way to calculate F, the force, tau, the time that it acts on the ion, and even V, velocity of the electron. Now EF can be calculated from say if we know the molar volume of the metal. D is an interatomic spacing, which again we can find from Google or physics handbook. So all this can be calculated, F and tau. Now coming back to what I want to do, I want to estimate this displacement. So I would be able to do that if I know, I might be able to do that if I know, say, the initial velocity with which it moves. Okay, because there is this force acting on it for a short time due to the electron. This impulse, force times time, would be the impulse, would cause a change in momentum on the positive ion, which is given by mass of the ion times, let me use a capital, okay, let me use V naught. I should call that VE for velocity of the electron. So I'll call V naught the starting velocity of the ion. Okay, so the impulse would allow us to calculate the initial velocity of the ion. The big M here would be the mass of the ion. So in principle, with this knowledge, we would be able to find the starting velocity. But how does that help? How does knowing the initial velocity of the positive ion help us to find this displacement? Well, it can if this displacement results in a simple harmonic motion. All right, we would expect that after this electron is gone and this is displaced, the positive ion would move back to its original position, and then it might overshoot and then it might oscillate a little bit before it stops. Now if that's the case, then we are looking at possibly some kind of a simple harmonic motion. Now, so if we know the starting velocity, we might be able to find this maximum displacement, which is the delta. So let's think about what we would need for such a calculation. If, for example, if I have a pendulum like that, say starting from here, okay, it takes off with a certain velocity v naught, and this is the maximum displacement. Let's say A, the amplitude. So how would the maximum displacement and the starting velocity, how are they related? Well, they are related by A times omega equals to V naught, where omega is the angular frequency of this oscillation. So that's the simple harmonic motion, a simple harmonic motion result. Now, and you see that we know how to estimate the starting velocity of the ion from these relations, but in order to find the maximum displacement, which is this, so this corresponds to the delta in our problem, we must know the angular frequency of this ion. Now there is a very simple way to estimate that maximum frequency. Okay, let's come back to this. If we look at these two ions, as the electron zooms past these two ions, both ions would get attracted. So they come together. Okay. Now as they come together, the surrounding electrons and ions become disturbed or displaced, and those would create a force that would pull them back to the rest position. Now, think about a wave that is propagating through this metal. All right, with a wavelength that is equal to, say, twice the interatomic spacing. Now I'm going to try and draw a picture of this to show what it looks like. Now, supposing that initially we have these ions in a row. Now, imagine a longitudinal wave going through this row of ions. So that will cause vibration in this direction. Now think about the highest possible frequency. Okay, that would happen when the wavelength, when we have the shortest possible wavelength, which would happen when, if it's a transverse motion, right, this would be the shortest possible wavelength, where this is displaced upward, this one down, up, down, up, down. But if you are talking about longitudinal wave, then this would be, say, moving to the right, and this moving to the left, right, left, right, left. Okay. So when this happens, we have the maximum possible frequency. Now notice that this motion, where the two ions come together, is very similar to that motion, right, where the two ions are attracted together by the zooming electron. So as a result, it's the same kind of displacement as this, and we would expect the same kind of restoring force. Now, and we actually know what this maximum frequency is for such a longitudinal wave. It is the dBi frequency. That's the maximum frequency for any vibration in a solid. So we actually know how to calculate the dBi frequency. And this is what we can use for this ion as after it gets displaced and the restoring force causes it to move back. Alright, so the angular frequency of this oscillation can therefore be estimated by the dBi frequency. So once we realize that, we can then make use of this pendulum relation to estimate the displacement delta. Now let's write down the connection. So V0, we now take V0 to be the initial velocity of the ion attracted by the electron. Amplitude would be the delta. Right, we are interested in delta as the maximum displacement of the ion up here. It's the maximum displacement. And then the angular frequency that we need is just the Debye frequency. So finally, we have all the equations we need to calculate delta. And from delta, we can therefore calculate the attractive potential. Okay, we are almost done. So now, there is one more detail we need to add, which is that this potential is not fixed. Okay, you can see that since delta is a displacement, after a short time, the positive ion would return to its original position, meaning that would become zero again and this potential will be gone. But we are interested in what happens, say, in a particular instant. We are interested to know what this potential looks like. And what we have here is a way to calculate this potential. But we are not interested in just what happens to the one particular ion. Okay, this electron, as it zooms past, would in fact leave behind a trail of displaced ion. So let's have a look at that. So we have these electrons zooming past. Now let's say the electron is here. Okay, so and there are two rows of positive ions on either side of this path. For example, when the electron is here, it might be next to some positive ions, but because the electron has just arrived, those ions might not be displaced very much yet. Okay, now for the ions which are some not too far behind, let's say that one, this ion would have experienced some force from the electron for a short time, so it would be displaced by a small amount, and the ion before that might have experienced the force for a slightly longer time, not slightly longer time, sorry. Let me say that again. The ion before this, alright, these ions, they would have experienced the impulse from the ion that zoomed past it, and they would be set in motion. Okay, so they would move by a small distance, and the ion even further back, likewise, but these ions would have moved for a slightly longer time than this ion, time being the time that the electron has moved from here to there, so they might move a little bit more. Okay, but as we go even further back, we would have ions that have already moved to its maximum displacement and perhaps start moving back. So the displacement would decrease. Right? Eventually, you reach the ions that have moved back to their original positions. So this is the picture that we would expect when an electron zooms past the positive ions. Okay, and behind those, we might expect the ions to have a little bit of remaining oscillation, but they might quickly die down. So we would be interested in how long this is, because all of these displaced ions would contribute to an attractive potential that might attract another electron coming this way. So therefore, it would be we would need to know what the length of this trail of positive ions is, in order to fully describe the potential. So if we look back at the potential expression that we saw here, the V there, this gives the potential at the maximum displacement. So in other words, it gives the potential due to this ion that has been displaced by the biggest amount. So for the other ions with smaller displacement, that would be a smaller V. Alright, so let's see how we might be able to calculate L. It's actually, we can actually make use of what we already know, that this velocity is V, say VE of the electron, and now if we look at this particular ion here, so once upon a time that electron was there. Okay, when the electron was there, these two ions, they would have just experienced the impulse, the attraction from the electron, just as those two are experiencing that right now. So when this electron was here, it would have just given the impulse to those two, and as this electron moves away, those two ions will start moving towards each other, and after reaching the maximum displacement, they would start moving back, and they would have arrived back at the rest position just when that electron reaches here. So therefore, the time that it takes for the electron to travel this distance, L, is the same as the time taken for this ion to move up and come back down to the rest position again. Alright. Now, and this time is actually the time for half a period of this oscillation. So the time for this to go up and come back down is the time taken, the same as the time for the ion to move over the length of this trail. Okay, so let me call this time, let's say the period of the oscillation is T. Alright, so this time would be the period divided by 2. And we know what the period is. The period is related to the angular frequency by 2 pi over omega d. So therefore, we know how to find L. L is equal to velocity times time. Velocity and time is T over 2. Alright, it's half a period. So this is equal, and T is 2 pi over omega d. So this would be V times pi over omega d. Alright, the 2 here would cancel out with the 2 there. So now we have we are now able to calculate the length of this trail and the maximum potential in the trail. So therefore we can sketch a graph showing this potential. Let's see, that's say that's R, okay, that's 0. Let's say that's the potential, that's the potential. Okay, if we think about the ions, they are displaced this way over a distance, over a length L. So we would expect that the potential is 0 there and there, but biggest in between. Now we also know that this is an attractive potential. Okay, so it has a negative value. The biggest and the most negative value would be around the center, and at the two ends they go to 0. It goes to 0, so this is what it looks like. Okay, and we know how to calculate this distance. Look at this. V is this, which has a minus sign there already. Okay, so this position here, this potential here is V. So now we know how to find an actual numerical answer for V and for L. So in principle, now that there is a potential, well, it should be possible then to use Schrödinger's equation to solve for a wave function due to this potential well. And indeed, it has been done by Cooper himself. And the solution to this Schrödinger's equation looks like this. So wave function R so just very roughly it looks like this. There are many oscillations, and the extent of this wave function is approximately the same as the extent of the potential well itself, and that's typically about 300 times the interatomic spacing. Okay, so this wave function, if you remember, is a wave function due to one electron, right, zooming past, creating displaced positive ions that then attract another electron coming towards the ions, towards the displaced ions. So in effect, it is a wave function for these two electrons. In other words, it's a wave function for the Cooper pair. Alright, of course each electron represents one, each of these wave function represents one electron. Okay, but the other electron would also have the same wave function, because it will also be attracted by displaced ions created by these electrons. So it's mutual. Okay. Now, when solving the Schrodinger's equation, we not only get the wave function, in principle, we also get the energy. Okay. Now, and as it turns out, it was found that this energy is approximately equal to Kb times the superconducting temperature. And that is very good, because it would seem that we now have an explanation for the superconducting behavior, or at least one aspect of it. Now suppose that this Cooper pair, this pair of electrons that can attract each other in this way, with the help of the displaced ions, of course. Suppose that this pair of electrons, which is now called Cooper pair, that they somehow make the metal superconducting. Suppose. Alright, we have not actually explained that part yet. Then if the temperature is too high, that would break up the attraction, break up the Cooper pair, and then it would stop being superconducting. Now the temperature where we would expect this to happen would be just the superconducting temperature, because we know that above the superconducting temperature, it stops being superconducting. Alright, so what this result suggests is that above Tc, Cooper pair breaks up. Okay, so that's fair enough. Now let's take this idea and work backwards through the list of properties of Cooper pair, or of superconductors, and see how much of those we can explain. I put a list here that I wrote down earlier. Let's see. I sort of listed 5 items. The last one is about this dependence of the Tc on isotopic mass, and that led to the idea that movements of the atoms somehow contribute to the superconducting property. So with this idea, we have worked out some details for the Cooper pair. We have worked out that the very idea of the Cooper pair. Now, and from this idea, let's move backwards, back up the list. Now, when we come to this property of the heat capacity, that below Tc, the heat capacity looks like the Boltzmann distribution function, which seems to suggest some kind of suggest two energy levels and therefore some kind of energy gap in between. Now we are ready to explain this energy gap. This energy gap, it could in fact be Kb times Tc, the energy of the Cooper pair. Or rather, we will call that the binding energy of the Cooper pair, since if it gains this energy because of the temperature, this kBt would be enough to break up the Cooper pair. Alright, binding energy in the sense that is the attractive potential energy. So now we have an explanation for delta. The two levels is basically for the lower one would be the Cooper pair. The higher level would be when they break up. So there we are. We have just explained the energy gap. And in fact, when a proper curve fitting is done to this heat capacity, the measured heat capacity curve, it has been found that the delta, the number in this exponential, is about Kb times Tc. Alright, so that the graph of C against T would agree with the experimental data. Okay, so we have roughly explained the behavior of the heat capacity. Now let's move to the critical magnetic field. So if the field is high enough, the superconductivity is destroyed. So how can the Cooper pair explain this? Let's look back at our wave function. So we have this wave function here. Now there is a detail that I've not mentioned in this wave function, and that is the spin states of the electrons. Okay, so this electron and this electron, which attract each other through the displacement of the ions, they can either be both spin up, or one can be spin up and the other one can be spin down. And it is the spin up, spin down configuration which has the lower energy, alright, and which allow them both to occupy the same energy states. That is the Cooper pair. Okay, so therefore it is the spin up, spin down combination that we should look at. So coming back to this property about the critical magnetic field, we would therefore expect a Cooper pair to have a spin up and a spin down electron pairing up. Now what happens if we apply a magnetic field to this? Then if the field is big enough, it would force both the spin to align with the field, to point in the same direction as the field. So this becomes like that and like that. But if this happens, then the two electrons can no longer be in the same state, and therefore the Cooper pair would be broken up. So this explains why there is a field, why when the magnetic field is big enough, it stops being superconducting. The reason is simply that the field breaks up the Cooper pair. Okay, that's nice. So moving back up to the Meissner effect. So if you recall, the explanation was that if all the electrons can go into the same state and form a giant wave function, that would be able to explain the Meissner's effect. So that was London's explanation. So now we can answer the question as to why all of the electrons can go into the same ground state in spite of Pauli's exclusion principle. It is quite simply because the electrons first pair up into Cooper pairs. So we spin up and spin down, combining to form a Cooper pair. Now once it forms they form a Cooper pair has zero spin because it's spin up and spin down. So it becomes like a particle of zero spin, and that is a boson. And we know that bosons, any number of bosons can go into a ground state. So therefore now we can understand why all the electrons can go into the same ground state. They do it simply by pairing up into Cooper pairs first, and thereby turning into bosons in effect. So therefore we have finally explained the problem, that problematic assumption in London's explanation for the Meissner effect. And finally, possibly the most difficult property to explain, and also the most obvious property, the zero electrical resistance. Now there is no very obvious way, like for the previous property, to explain this using the Cooper pair, but there is a qualitative way, which is that if you recall from this picture about the wave function and the potential well, that a Cooper pair has a typical size of about 300 times the interatomic spacing. So that is really huge in atomic terms, right? So what this means is that we would expect there to be a lot of overlapping of the Cooper pairs. So in that sense, it is as if we have lots of Cooper pairs that are closely packed together. Okay, right, Cooper pairs that are 300 times the spacing between atoms. So when they're so closely packed together, it's like the situation we have in liquid helium-4, where the atoms of the liquid would, of course, be closely packed. Okay, and we remember what happened in superfluid liquid helium-4. Now the reason why it can behave like a superfluid is because, if you remember Landau's explanation, right, that the dispersion relation looks like this. It has phonon excitation and it has roton excitation. But if we look at the more basic reason why it has these, say why it would have phonon excitation. It has to do with the fact that the helium atoms are closely packed, which is why we can have this wave-like displacements traveling through it, which are quantized into phonons. Okay, so we can't have phonons if the atoms are not closely packed. So we can think of the close packing of the particles as the basic reason why phonon or even protons exist. So one possible way, even if it's qualitative, is to think that this close packing of the Cooper pair leads to similar behavior to liquid helium-4, in that it could lead to properties of Cooper pair phonons and Cooper pair protons. And if that is the case, then we would have a corresponding Cooper pair superfluid and Cooper pair Landau's critical velocity, below which movement of the Cooper pair superfluid would experience no resistance. So that gives us a very qualitative explanation of why a superconductor can have zero electrical resistance. So we'll stop here.